Well, so let's begin.
Экран видно, да, мою демонстрацию?
Yes, we can see your presentation.
Сейчас, секундочку, извините, я настрою. Topic of my today's talk is Hopf invariant, and let's start from the definition. Let's fix the generators in the top cohomology groups of the S2k-1 and S2k. Let k bigger than 1 and f be a continuous map from S2k-1 to the sk. So we have the con of the map f, such as the form sk glued by f with d to k, and the cohomology of Cf so equals to that if I is 0k or 2k and 0 otherwise. Let A be a generator of the group HK of Cf and B generator of H2k of Cf. So a square belongs to the H2k of Cf, and then there exists a integer number h of f such that a square equal to the h of f times b. That's number h of f called the Hopf invariant of the map f, and note that if k is odd, there we have that a square is 0 by the skew symmetry of the multiplication. Then Hopf invariant of the map of the any map f is 0. So Hopf invariant is trivial if k is odd, and from that moment we will.
What happens when k is 1? You say that k is greater than 1, and what happens if k is exactly 1? Well, then 2k minus n is also 1. So basically, what prevents us from considering this case?
In this case,
so we take a map from S1 to S1 of degree n. We can form the cone, and the result would be a Moore space. The first homology would be z by n, and the rest of them would be 0. So it's no longer true that hi is z in those degrees are 0, so 0 elsewhere. Hi will be z by n in degree 2 and 0 elsewhere. Okay.
And the second notion that if map f1 homotopy to the map f2, therefore cons homotopy equivalent, and we have that Hopf invariant of the map f1 coincide with Hopf invariant of the map f2. And we can think about H as a map from P4n-1 of S2n to Z. And lemma H is a homomorphism. Proof firstly check that trivial element maps to the trivial. Con of the constant map is a wedge of spheres of dimension 4n and 2n. Therefore, H of E equals to 0. So we want to show that Hopf invariant is additive, and to see that we compare the con of the maps f plus g and con of the map f wedge g. That by that has the form S2n glued by f wedge g with wedge of d for n and d for n. So we have the quotient map from C from the cone of f plus g to the cone of f wedge g that collapse the equatorial disk. And let a f plus g be a generator of h2n of c f plus g, b f plus g generator of h4n of c f plus g. Cohomology of the cf wedge g is z square if e equals to 4n, and let's generate bf and bg. That's pullbacks of the generator of h4n of cf and cg by the inclusion of cf cg to the cf wedge g. H2n of cf wedge g equals to z, and if e equals to 0, so we have that.
Could you perhaps enlarge your slides? We can better see the notes.
Мгм. Сейчас, секундочку, у меня почему-то не получается. Вот.
Yes, well, I think it's better.
So note that Q star of AF wedge G is AF plus G because Q star is because Q is a homomorphism in of CF plus G to C to the to K scalet of CF plus G and C to to n scalet of the CF wedge G. And Q
Skeleton.
skeleton. And Q star of BF equals to the Q star of BG equals to the BF plus G. Therefore, we have that A square of F AF plus G equals to the Q star of A square of F wedge G equals to the Q star of H of F times BF plus H of G times BG. Therefore, that equals to the H of F plus H of G times BF plus G. So we proved that Hopf invariant that homomorphism. Let's check that Hopf that is homomorphism not non-trivial when K is even. So we want to check that there exists f from P for n minus 1 of S to n such that Hopf invariant of f is 2. To see that, note that cohomology of product of spheres of dimension 2n and 2n is z when I equals to 4n, and let's B prime is a generator of that group. Z square if E is 2n, and let A1, A2 be Poincare dual to the component of the multiplication. And that if I 0 and 0 otherwise. Define space X as a quotient of the product of spheres by the relation that x0 equivalent to the x0x. Note that x has a three cells of the dimensions of 0, 2n, and 4n. Therefore, x has the form S2n glued by some map f with d4n. And let Q be a factor map, quotient map from S2n times S2n to x. And also B is a generator of H4n of x, A is a generator of H2n of x. So we have that Q star of B is B prime, Q star of A is A1 plus A2, and we have the chain of the equalities that H of F times B prime equals to the H of F times Q star of B equals to Q star of H of F times B. That equals to the Q star of A square by the definition of Hopf invariant. And that equals to the A1 square plus 2A1 A2 plus A2 square. First and last summand is 0 because a1 square and a2 square is 0 in cohomology of the product of spheres, and a1 a2 equals to the b prime. Therefore, we show that h of f times b prime equals to b prime. So Hopf invariant of the map f is 2. And the main goal of my today's talk is prove the following theorems. First, there exists f from p2n minus 1 of Sn with Hopf invariant 1, if and only if n is 2, 4, or 8. Second, that Rn has a division algebra structure if and only if n is 1, 2, 4, or 8. Next theorem is Sn minus 1 is parallelizable if and only if n is 1, 2, 4, or 8. And the last theorem is Sn minus 1 is H-space if and only if n 1, 2, 4, or 8.
Why is, sorry, there's something not quite right here. Why is S2 an H space? Okay, no, okay, 2 minus 1 is 1. Okay, 1 minus 1 is 0. Okay, yeah. And then 4 minus 1 is 3, and 8 minus 1 is 7, yes.
Yes, and firstly, say that for theorem 1, 4, we know the implication from the right part to the left part, that standard construction with projective planes. And we prove the series of implications from the left parts of the theorems, such that from theorem 2 to theorem 4, from 3 to 4, from 4 to 1, if n is not 1. And the last step is proof of the theorem 1. And firstly, note that theorem 2 equivalent to the following. Rn has a division algebra structure if and only if Rn has a division algebra structure and a trivial element. Let's prove the notion. Let E be an arbitrary vector from Rn, and we can assume that E square is E. Because we can define new multiplication B such that B of xy is e to the power minus 1 times xy. That's new multiplication has no zero divisors, and it is a bilinear map from Rn times Rn to Rn. Let's define alpha and beta from it is a linear maps from Rn to Rn. That's alpha maps x to xe, and the beta maps x to ex. And note that kernel of alpha equals to the kernel of beta equals 0 because e is not a divisor of 0. And define new multiplication b from xy as alpha to the power minus 1 of x times beta to the power minus 1 of I. That's new multiplication has no zero divisors and is a bilinear map. So we want to check that E is a trivial element.
Could you return to the previous page, which contains the plan? Okay, so 2 implies 4, 3 implies 4. Okay, yes, and then 4 implies 1, yes, and then we prove this one. Okay, very well.
So b of xe by definition is alpha to the power minus 1 of x times beta to the power minus 1 of e, but beta to the power minus 1 of e is e because e square is e, and we have that equal to the alpha to the power minus 1 of x times e. That's by definition of alpha of alpha to the power minus 1 of x, and it is equal to x. And the same for b of ex. Okay, so let's start the proofing of the implications. First, from 2, 4, 4, let's Rn
From
has a
2
division.
to 4. Если второго, значит, к четвертому. 2, 4.
From 2 to 4, yes, thanks. If Rn has a division algebra structure with a trivial element E, let's xy from Sn minus 1 in Rn with a standard Euclidean matrix. So define mu of xy as a xy divided by norm of xy. Definition is correct because norm of xy is not a zero, because norm of x and norm of y is not a zero. And our algebra structure has
What's the norm?
standard Euclidean norm.
Okay.
And our algebra structure has no zero divisors. So mu of xe equals to the norm, x divided by norm of x equals to x, and the same for mu of ex. So Sn minus 1 is H space. Because E is a trivial element that we show in.
Yes. Hold on. What is mu? Mu is the multiplication.
Yes, we define the multiplication.
So we want we have multiplication, and we want an H space structure.
Yes.
We already have a multiplication, and we define a new one. Is this correct?
Yes, yes. Multiplication on Rn define mu.
Okay. Okay. So we want to show that this is an H space, which follows from the fact that we have a strict unit in the algebra.
Yes, yes.
Okay.
Next implication is from 3 to 4. Let's Sn minus 1 is parallelizable. Then we want to show that Sn minus 1 is also H space. Sn minus 1 parallelizable, then there exist vector files, linearly independent
Fields.
vector files v1 fields v1 vn minus 1 on Sn. By Gram-Schmidt orthogonalization process, we may assume that for every point x, vi of x orthogonal to the vj of x, if I is not j. And in the point e1, where e1 so on en is a standard basis in Rn, e1 of vectors e1, v1 of e1, so on, vn minus 1 of e1 is a standard basis. So for every point x from Sn minus 1, there exists a unique alpha x from SON such that alpha x maps the standard basis to the basis x v1 of x, so on, vn minus 1 of x. And define mu of xy as alpha x of y. Let's check that is a H space structure. Mu of e1 x equals to the alpha e1 of x. And that equals to the x because alpha e1 is ID by the definition of vector files in fields in point e1. And mu of x e1 is alpha x of e1, and that equals x by definition. Also, but by definition. And the next implication is from 4 to 1. Let's Sn minus 1 is H space and n is not 1. We want to show that there exists f from p to n minus 1 of Sn with the Hopf invariant 1. And to show that we want to construct the map f from S2n minus 1 to Sn, that's we'll have the Hopf invariant one by the multiplication mu. Okay, let's represent Sn as a union of the two disks d plus and d minus glued by the boundaries, and the Sn minus 1 is a boundary of dn times dn, so that has a form ddn times dn glued with dn times ddn, and define a map f from S2n minus 1 to Sn.
Sorry, and what is okay? So we assume that Sn minus 1 is an H space, and okay.
Okay, so define f from S2n minus 1 to Sn. Define for every point for point xy in the first component of the union. Define f of xy by the following formula: norm of x times mu of x divided by norm of x y, and that point belong to the dn plus. And the same formula for xy from dn times dn. Firstly, we want to check that f is continuous in every component of the union.
Component.
Можно еще раз?
Component.
Component.
Ударение на второй слог. Component.
Спасибо, понял. Component of the union. And we need to check continuously only when x is 0, and if x tends to 0, so f of xy tends to 0 in d plus, so f is continuous in every component. So we need to show that f is continuous everywhere. We need to check that maps coincides in intersection. If xy belongs to the ddn times ddn, therefore f of xy equals to the mu of xy from in d plus, and same for xy in dn minus. But that point coincide in Sn, so f correctly defined and continuous as a map from S2n minus 1 to Sn. And we need to check that Hopf invariant of f is plus minus 1. Okay, let's define a map phi from D to N to CF is be a characteristic map of 2n cell. We can see on phi as a maps of pairs ddn time.
We can look at, or we can view phi as a map of pairs.
We can view at f as a map of pairs, dn times dn and ddn times d to cf and d plus. Same for d minus, and note that phi restriction of phi on dn times e and e times dn is a homomorphism from dn times e to dn minus correspondent. So we need to check that first upper horizontal map is surjective.
Surjective.
To see that, let's see on the following commutative diagram where horizontal maps.
Let's look at the only option is look at. See at the videos. Давайте увидим диаграмму. Well, it's comprehensible, but sounds strange. Let's look at. Давайте посмотрим.
Let's look at the following diagram. Following commutative diagram. In cohomology, so note that that vertical map is isomorphism because D plus and D minus are contractible in CF. That map induced by phi and note that the composition of that two maps is isomorphism because that's composition induced by restriction of the phi on the on the dn times e. So that composition is isomorphism in the first component of the product and in the second component of the product. Okay, that map is isomorphism by the exact sequence of the pairs, and that map also
Also,
is isomorphism. Also, isomorphism. So our map is a composition and particularly is surjective. Group is B tensor B. Generator of the right group is A, and B tensor B maps to plus minus A. So by definition of Hopf invariant of F is plus minus 1.
okay. Could you make your slides full screen again? Yes. Oh, looks better.
So last step is prove the theorem that there exists F from P for the 1, 2, or 4. And to do that, I want to define the Adams operations. Let EI be a standard symmetric polynomials from the variables xi, where I from
In the
1 to
variables.
infinity.
Значит, от переменных. In the variables.
In the variables xi. And let Ni be Newton polynomials that's nk equals to the sum from I equals to 1 to infinity xi to the power k. So by theorem about symmetric polynomials, there exists a unique polynomial pk from t1 tk such that nk equals to the
And what's the ground ring?
k from I think q. Good for us. Was it?
Well, if we want to express the Newton sums in terms of the elementary symmetric polynomials, well, we could take any commutative ring to be the ground ring. If we want to go in the opposite direction, then all primes must be invertible.
Okay, then there exists a unique polynomial pk, and let C be a complex vector bundle, and we define a new vector bundle over same base x, pk of xi, by the formula pk of the xi of xi equals to the pk of xi lambda xi, so on lambda k of xi. And start showing some properties of the pk that pk of xi plus eta equals to the sum of pk of eta and pk of xi. To do that, firstly, the similar pk set of variables is a set of variables xi is a disjoint union of the variables yi and zi. So n r of x equals to the r of y plus n r of z, and the e equals r es of y times et of z. So by definition of pk, we have that pk of e1 ek of y equals to plus pk of e1 ek of z equals to the pk of sum of s plus t equal 1 e s y e t z. So on s plus t equals k e s of y times e t of z. Therefore, by theorem about symmetric polynomials, pk of any pk of alpha 1 alpha k plus pk of beta 1 beta k should be equal to the pk of following sums.
By the way, this psi k of psi lives where? On the previous page, we defined psi k. It's a map from vector bundles to where? So this psi k lives where?
Pk of xi is also a vector bundle.
Well, this would be true if all coefficients of pk were positive.
In k
or at least non-negative.
Yes.
So the result is this pk is to be understood as an element of the K theory of the base, and the question is it reduced, non-reduced? What is it? Значит, результат операции пси живет в какой-то категории, потому что мы не знаем, что коэффициенты полиномов ПК не отрицательны. Может быть, они не отрицательны, мы просто пока не, значит, ну, в данную секунду мы это не знаем. So we have something which is an element of the Grothendieck ring of the category of vector bundles, or in other words, k0 of x, where x is the base space. То есть вот этот вот результат операции ПСК, он лежит в категории, ну, значит, потому что мы хотим иметь возможность вычитать расслоение. А в категории как раз мы это умеем.
Okay. So let's substitute to the variables alpha s vector bundle alpha s lambda s of xi, and to the beta t lambda t of eta. We know that formula, and therefore we have
well, in this formula we also need to prove that psi k of epsilon is what is it? Is epsilon.
Yes.
Why do we have?
Is epsilon in K theory? Because
is it epsilon, or or the sum of k epsilons. This is well. Let's have a look at the previous page.
Mm.
What happens if we substitute epsilon? Well, we get epsilons. We get the epsilon at the first place, and then we get zeros. No, sorry. In this formula, psi is the same as lambda 1 of psi. Значит, в формуле после кси идет лямбда в квадрате, потому что кси это лямбда кси. Лямбда 1 от кси.
Yes. If we substitute the epsilon n, we have that in right part we have some and differences of trivial vector bundles, and that is a trivial element in K-theory.
Well, it's well, the additive identity is 0, and the multiplicative identity is epsilon 1. Значит, в категории значит, 0 это нулевое расслоение, это мультипликативная единица, это тривиальное расслоение ранга 1. Замечательно. So what do we get if we substitute 1, 0, 0, 0 in pk?
Lambda k of 1 is 0 because 1 is line. Then
значит, Андрей, значит, вопрос был другой. Что будет, если мы в полином bk, ну, который, в принципе, можно посчитать, поставим 1,0,0000?
It is a 1. Yes. It is a...
Значит, ПК это полином от, ну, значит, там просто полином в кольце, значит, полиномов от К перемен. Ну, значит, что будет, если мы вот сделаем такую постановку? Значит, там мы хотим выразить, значит, сумму Ньютона через элементарно симметрический. То есть, so we
Just, ну, вопрос, что будет, если мы поставим в ПК единицу и все остальные нули, да?
Да.
Ну, у нас получается единица. Единица в степени k, единица.
Единица или k? Вот давайте поймем.
У нас получается, кажется, просто единица в степени k, то есть единица.
Ну, тогда формула на следующей странице неправильная. Вот, давайте посмотрим теперь на следующую страницу. Значит, вот следующее, значит, мы доказали, что псика аддитив. Хорошо. Значит, дальше в формуле значит, псика, значит, эпсилон, да, значит, эпсилон n это эпсилон 1 n раз, правильно? То есть это такое аддитивное, значит, аддитивное. Значит, получается, что это значит, эпсилон, значит, ну, опять же, аддитивно, значит, n раз. Значит, его результат не сходится. Давайте смотреть. So we we need to think a little.
Pk of epsilon is epsilon, and from additivity we have that pk of xi plus epsilon n times is pk of xi plus epsilon n also.
Okay, well, then this agrees with what you say on with what you've just said. Anyway, so it's an exercise for shipping and for everyone that's listening to check that this formula is the last formula is correct.
Okay. Okay. And also note that if also note that y is if f is a map from y to x and xi is a vector bundle over x, f star commute with lambda k, and because pk is a polynomial of lambda k's, we have that pk commute with f star, and we have the first commutative diagram, and by applying map to the point to x and y, we have the similar diagram for reduced k-theory of x and y. And to prove the next properties of Adams operation, I want to formulate without proof the splitting principle. Let E is a complex vector bundle over a compact Hausdorff space X. So there exists a compact Hausdorff space f of E and map P from f of E to X such that P star is injective and P star of E is sum of line bundles. Okay, next lemma, next property of Adams operations is if L is a line bundle, then we have that pk of L is lambda k. By definition of pk, we have that pk of L equals to the pk of L and zeros because other exterior powers of L is zero. And pk of t1 and zeros equals to the t1 to the power k. So we have that formula. Next property is pk is multiplicative. Firstly, show that for cases when Xi and eta is the sums of line bundles, let Xi is the sum of Li and eta b is the sum of Li prime. So pk of tensor product of Xi and eta equals to the pk of sum by E and G Li times Li prime equal to the sum of Li Lj prime to the power k by the previous lemma. And therefore it is equal to the sum of lambda I to the power k tensor product with sum of lambda I prime to the power k. First sum is a pk of xi by the lemma by the first lemma and additive of the pk. Second sum is also equal to pk of eta. For orbital xi and eta, let P1 is a map from the splitting theorem from space f of xi to x, and P2 is
Значит, важное замечание по поводу английского. Let something be. Вы знаете, у Beatles есть такая песня Let it be. Вот они говорят let it be, но они не говорят let it is. Они говорят let it be. Вот, значит, вот давайте мы будем учиться у Beatles. Let psi be an Adams operation, and so
on. Okay. Let P1 be a map from the splitting lemma from f of xi to x, and p2 also a map from the splitting lemma from f of p1 star of eta to f of xi. Note that composition of p1 star and p2 star is injective, and p1 star, p2 star, p1 star of xi and p2 star, p1 star of eta is a sum of line bundles. So for p2 star, p1 star of xi and p2 star, p1 star of eta, we know the additive property. We can, by neutrality of pk, we have that p2 star, p1 star of product equal to the p1 star, p2 star of pk of the product. And because composition of p2 star and p1 star is injective, я перепутал. Because p2 star, p1 star is injective, we have that pk of xi tensor pk of eta equal to the pk of xi tensor with eta. Next lemma states that composition of pk and pl is a pkl. Proof also let xi be a sum of line bundles. So we have that pk pl of xi equal to the pk of sum li to the power l equal to the sum of li to the power kl, and that equal to the pkl of xi. For arbitrary xi, let p be a map from the splitting principle from f of xi to x. Therefore, we have that pk pl of p star of xi. P star of xi is sum of line bundles equal to the pkl of p star xi. So p star of pk pl of xi equal to the p star of pkl of xi. And by injectively of p star, we have that pkl of xi equal to the pkl of xi. Pk composite with pl equal to the pkl. Next property is if p is prime, then cp of xi equals to the xi to the power p by module p. By definition, that means that there exists eta from k theory of x such that xi1 plus p eta equal to the xi2. And the proof firstly checks that condition for sum of line bundles. So we have that xi equals to the sum of li, therefore cp of xi equals to the sum of li to the power p. But sum of li to the power p by module p equals to the sum of li to the power p. And more
Modular.
modular
By modular.
modular p. And we can note that pk of xi minus xi to the power p equals to the p times q of xi, where q is some polynomial because the difference of the left part as a monomial of li is symmetric, and the powers of xi is basis in symmetric polynomials. So if xi now is an arbitrary vector bundle over x, we have a map q from f of xi to x. So we have that pk of q star of eta minus q star of xi to the power p equals to the p times q of q star of xi. And that equal to the q star of p times q of xi. Therefore, by the injectivity of Q star, we have that pk of Xi minus Xi to the power P equals to the P times Q of Xi. Next lemma, pk is multiplicative by external multiplication. So we want to show that pk of alpha external product with beta equals to the pk of alpha external product with pk of beta. So pk of alpha times beta equals to the pk of p1 star of alpha times p2 star of beta, and that equals to the p1 star of
What's the external product of the vector bundles?
External product of vector bundles is let we have
Let us have
let us have the xy c eta. So over xy we have bundle p1 star of xi tensor product with p2 star of eta.
Okay, this is the same as
that element.
this is the same as psi tensor eta. So let's write it down. Значит, вот напишите, пожалуйста, там под вот этой формулой, что вот то, что написано, то, что подчеркнуто, это кси звездочка это.
Понял.
Okay.
Okay, that equals to the p1 star of pk of alpha tensor product with a p2 star of pk of beta, and that equals to the pk of alpha external product with a pk of beta. So we show the following properties of Adams operations.
We have shown. Значит, мы не доказываем, мы доказали. Let's make it clear. So we have shown. Напишите это, пожалуйста, еще кем после в конце слова shown. We have shown. Хорошо. Eva.
Next lemma, pk as an operation in the reduced k-theory of S to n is just a multiplication by k to the power n. And proof, firstly, check in the case when that property in the case when n is 1. So reduced k-theory of S2 generated by alpha equals to the h minus 1, and pk of alpha equals to the h to the power k minus 1, because h and 1 are linear bundles. That's equal to the 1 plus alpha to the power k minus 1. But alpha in the power 2 is 0, therefore that's equal to the k alpha. And if n bigger than 1, then we have the isomorphism of tensor product of reduced k-theory of S2 times reduced k-theory of S2 n minus 2 to k-theory of S2n. That maps element alpha beta to the external product of the alpha and beta. as we shown is in the in last time lecture, external product can be, we can think about external product as a operation from the uh, uh, multiplication of k-tiers to the k-tier of the smash of the products. So it is, we have shown that is isomorphism, and the pk of alpha external product with beta equal to the pk of alpha external product with pk of beta equals to the k alpha external product with k to the power n minus 1 of beta by the induction. And that equals to the k to the power n of times external product alpha and beta. Okay. And now we want to end proof of the theorem 1. We have the for we have the exact sequence of the pair in the reduced K theory for Z maps. Note that K1 of S4n and the K1 of S2n is 0, then this element is 0, and this group is 0. And let B beta from reduced K theory of CF is an image of the generator of reduced K theory of the S4n, and the alpha any preimage of the generator in reduced K theory of S2n. Note that alpha square maps to 0 because square of the generator of Z group is 0. So by exactness, we have that alpha square equals to the h times beta. And applying the Chern classes, we see that h times b equal to the a square. And we have that h equal to the Hopf invariant of f, and it is equal to 1.
Okay, so here we use the Chern character, which is a map from the K theory of X, not tensor Q, to the completed cohomology ring, and we with rational coefficients, and we assume that this Chern character is in fact a map which preserves both the plus operation and the product operation, and moreover, it's in fact an isomorphism. If we basically, it's an isomorphism between the rational K theory and the rational cohomology, which does not preserve the degrees, but it does preserve even elements and odd elements. Okay. So, well, let's just point out that here we use the Chern character, and it's not too difficult to check its properties, but it requires some work. Okay.
So note that pk of beta equal to the k to the power 2n times beta because beta is image of the generator of image of the element in k theory of S4n, and the pk of alpha equals to the k to the power n times alpha plus some integer μk times beta times beta. And let's compare the psi2 composition with psi3 of alpha and psi3 composition with psi2 of alpha.
And what is mu1? Sorry, what are mu2 and mu3 in this? Oh, okay. Yes. Yes, I see now. Very well.
So we have the Z equality and Z equality. Note that by the one of the properties of pk, we know that p2 of alpha modular 2 is equal to the alpha square and z equal to the beta. And also p2 of alpha equals to the 2 to the power n times alpha plus mu2 times beta. So that element is 0 by modular 2. And we understand that mu2 should be odd. So from that equality, we understand that 3 to the power 2n minus 3 to the power n should be divisible on 2 to the power n. And
divisible by
2 to the power n. And so 3 to the power n minus 1.
What divides what? Is it 2 to the n which is divisible by 3 to the n minus 1, or the other way around?
Сейчас, можно еще раз? Я, может, сам запутался в каком-то порядке.
Что делится на что?
3 в степени n минус 1 должно делиться на 2 в степени. Потом что-то мимо.
Okay. So let's explain. Значит, давайте припишем к троеточию. Значит, что это троеточие означает is divisible by. Нет. Ну, хорошо. Вот. Давайте тоже обведем в квадратик, чтобы не потерялось.
Что еще раз?
Давайте обведем в квадратик. Вот один квадратик эквивалентен значит, другому квадратику. Very well. Okay, so well, that's it's not too hard. Well, let's prove this.
Let represent n as in the form 2 to the power l times m, where m is odd. And first case, k is l is 0. Then we have that 3 to the power m by module 4 is minus 1. And so m should be less or equal 1. Next case, when l greater than 1. By induction, we want to show that the highest power of 2 in the 3 to the power n minus 1 is l plus 2. And base when l is 1, 3 to the power 2m minus 1 is such product. Highest power of 2 in the first bracket is 1, as we show, and highest power of 2 in the second bracket is 2, because 3 to the power m plus 1 by module 8 is 4. So we want to show the induction step of induction. 3 to the power n minus 1 equal to the 3 to the power n divided by 2 minus 1 times 3 to the power n divided by 2 plus 1. By induction, the highest power of 2 in the first bracket is l plus 2, and in the second bracket is 1 because L plus 2 bigger than bigger than 0. So we have that um, so how highest power of 2 the 3 to the power n minus 1 is L plus 2, and that should be bigger than n, and n equal to the 2 to the power L times m. So L is 1 of 2, 1 or 2, and n belongs to the 1, 2, 4.
Okay, very well. Are there any questions? Let's fix the word highest at the top on the right. This word is spelled Highest. Highest. Yep. Very well. Andre, please send me the revised notes, and I'll post them on the web page.
Mm-hmm.
Okay. Are there any more questions? Well, in this case, I'll stop the recording